Now it's time to gather another set of definitions. A statistic is a descriptive measure of a sample, most often numerical. Now that's not statistics. Statistics is the science of collecting and organizing and all of that. But a statistic is a number that you gather about the sample. So, for example, the average age of a sample of statistics students, or the proportion of a sample of statistics students that prefer early morning classes, right? So, those are numbers that describe those groups. A parameter is a descriptive measure of a population, again, most often numerical. So, if you think about the average age of a sample of statistics students is a statistic because it's from a sample. But if you have the average age of all statistics students, that's a population, right? So that's the sample, that's a population. Or if I wanted to know what proportion of students prefer early morning classes, from a sample, that's a statistic. But from a population, it'd be all statistics students. What proportion of all of them prefer early morning classes? See the difference? All right, now one other topic to think about is the process that it was discussed kind of in that definition of statistics, because it said we would collect, organize, summarize, and analyze information. But this is kind of how it works. So you design your study. You think about what you're interested in. Say the average age of statistics students. So if your goal is to find the average age of statistics students, that's you identify that goal. You figure out your population, which is all statistics students. Then you gather a sample from that population, like some statistics students. So let me give you this example as we go. So if this is all statistics students, then this sample would be a nice, random, unbiased sample of statistics students. Right? It's important to be unbiased because otherwise we've got problems. But that's your sample. So then you draw that sample from that population. Then you ask them, hey, do you prefer early morning classes? What's your age? Right? So you would gather that information, and from there you would either gain the average age, which we'll talk about average. There's a couple symbols for that. But for us, the most important symbol for average will be X bar. For proportion, it'll be P hat. So what proportion of you like early morning classes? That'll be P with a little hat on it, P for proportion, right? And they have these little things on the tops of their heads to show that they're from a sample. And then we would gather and infer, okay, if the average age for my class is 22, then I assume that's the average age for all the population. And that would be the population parameter. And you would draw that conclusion and go back to the population. And the average there, again, we'll learn, there's a few averages, but the most important for us will be mu. And X bar and mu are related to each other. This is from the sample, that's from the population. We'll talk about that in section 3.1. And then for proportion, it's just P for proportion, right? Now I'm going to put little quotes on average. Average is a little bit of a sticky issue because the one I'm specifically using here is something called the mean. But there are other averages. So, and you could do the same thing with other averages. You could do it with the median. Technically, you could do it with the mode, although I wouldn't recommend it. But there are the mid-range. There are other values of average. But again, the most common one we are going to use is the mean. And X bar is the symbol for a sample mean. Mu is the symbol for a population mean. More on that in section 3.1. But that's the process. You figure out what you want to know, who you want to know it from, right? So who do you want to know about? Gather a sample, collect data on them, make inferences, right? And then you go, well, I think the average age for all of this population is 20 or whatever. Now keep in mind, when you take that sample, no matter how good it is, even if it's random and unbiased, you're still using a sample to estimate, which means you'll never be perfect. So what that's talking about is when you take this draw right here, that is always a smaller group than it was to begin with. And so that means that when you make this inference down here, this is never perfect. It has something called sampling error. just due to the fact that it's a sample, right? Because you take a sample, because you are taking a subset, so smaller subset. Once you do that, it's never a perfect representation of the whole population. If you want the whole population, you take a census, right? A census is supposed to be the whole population, although the US Census never gets there, but that's a whole other discussion, right? So drawing that sample, getting that smaller group, introduces something called sampling error. Now, the larger the sample, the smaller that error is going to be, hypothetically speaking. So the US Census takes a very large sample of the American population. It's not full sample, but it's not the full population, but they try. And so therefore the sampling error is relatively small. All right. Then just something to keep in mind. If the population is the whole group and you're taking a subset, that means that you can get to know what these two values here are. Like I'll know if I poll my class, I'll know what proportion of them prefer early morning classes. I'll know their average age. I mean, within reason, as long as nobody's lying to me, right? That will be known to me. What's unknown is the larger value, these two values over here. I don't really know what those are. I can take a guess that they're close, right? But I don't know for sure, right? So that's just something to keep in mind, that that leap from the known part of my sample to the unknown part of my population, that's what chapters 9 and 10 and 11 are going to help us do, right? So when we do that, it's going to be tricky, but we're going to make it happen. But nevertheless, it's going to be difficult to do, and it's also a little bit mind-bendy because you never really know what this value is. You just know where you think it is. But nevertheless, that value is a constant. There is some average age of all Jackson College stats students. It exists. I just don't know what it is, right? Now, the other thing about these statistics over here, if I get one sample from one class, that would have an X bar, that would have an average for that class. But if I go get a second class, it would be different, right? I mean, they should be close to each other, relatively speaking, but it will be different. And so that's what this is saying. So this is saying it's different for every sample. Which is also a little bit of an issue. That's also a piece of what sampling error is. Sampling error is that your sample is never perfect representation of your population. And of course, every sample is slightly different, right? So that's also the beginning of sampling error. This is some unknown constant. I just don't know what it is, but it exists. Now, one other thing to keep in mind before we head off to an example is that variability is very important. If every student was exactly the same age, there'd be no point in statistics at all as a field, right? Because all values would be the same. If there's no variability, everybody's exactly the same. And that's boring, right? So we study variability because we study how samples are different from sample to sample. That's chapter 8. And also how individuals are different from person to person, which is really in chapter 3. So that variability in chapter 3 and chapter 8 is why we have a subject in the first place. Because if everybody was exactly alike, there'd be no point to this, right? And it doesn't have to be people. I mean, it could be whales. If every humpback whale was exactly the same size, there'd be no point in studying them. But of course, they're different. They have different calls. They have different sounds. They have different everything. And that's what we study, because that variability is what makes it interesting and makes it worthwhile studying. And a little hint to you is that pretty much everything has variability, even things that are trying to be similar to each other. All right, yet again, these definitions don't really mean much unless we have an example. So let's put an example with them to help us. A drug manufacturer is interested in the proportion of persons who have hypertension, which is elevated blood pressure, that's what that word means, whose condition can be controlled by a new drug the company has developed. A study involving 5,000 individuals with hypertension is conducted. Of course, they would never give it to people without hypertension. There's no point to that. They're giving it to people with high blood pressure. And it is found that 4,000 of the individuals are able to control their hypertension with this drug. Okay, wonderful. So what's their research objective? Right, what's their goal? Well, they obviously want to know what proportion of people are helped by this new drug that they invented, right? So their goal would be find the proportion of people with a hypertension whose condition can be controlled by this new drug. It's like it's already in there. Whose condition can be controlled. Condition can be. It won't always be so spelled out, but. All right, now what was the sample? Well, the sample was the 5,000 individuals right there with hypertension. So it was 5,000 individuals with hypertension. Now, who does the drug company want to sell this drug to? Well, all people with hypertension, right? So that's the population, all people with hypertension, because of course they would like to sell it to everybody. That would be great. And an individual is any person from that population. So anybody, right? Any person with hypertension. All right, now they gave us enough information to figure out a statistic. They told us that of the 5,000, 4,000 of the individuals were able to control their hypertension with the drug. So that's a p hat, right? That's a proportion. And it's from a sample, so it gets a little hat on its head. So it was 4,000 out of the 5,000, right? Which is 0.8, but in case you don't believe me, 4,000 divided by 5,000 is 0.8. Or if you prefer Desmos, right? No problem. 4,000 divided by 5,000. There you go. Okay, so that is a sample proportion. So it was 0.8, which would be better written as a percentage for our terms of understanding. So 80% of the sample was able to control their hypertension with the drug. Because hypertension is something you just manage, right? You have to have blood pressure, otherwise you're not alive. But you don't want it to be high. So hypertension means it's above what you should have it at. Their hypertension. Okay. So then what's the parameter? What is this an estimate of? So 80% is really your statistic, and this is just kind of explaining what that is. So 80% is the number, or 0.8. I mean, technically, either one. The 80% just is an easier way to explain it. Well, what they want to know is what proportion of all the people, right? So that's what they're looking for, finding that proportion. So they want to know, describe P. P is the proportion of all people, right? Because it's from a population with hypertension that could control it with the new drug. It being the hypertension. Now, of course, we don't know the value of this parameter. So that's the answer to this next question. No, the parameter is unknown. Why? Well, because we didn't give the drug to everybody, right? To know the parameter would mean I have to take all people on the planet, in the country, something like that, and give them all this drug. So parameter unknown because we did not give, or the company, I guess. It's not us. We're not doing it. The company did not give the drug to all people. And let me just reiterate what I said on the previous page. The statistic is known. We know 80% of that sample was able to be helped. Their hypertension was able to be helped by this new drug. We don't know the parameter. There is some percentage of all people with hypertension that would be helped by this new drug, and we don't know what it is. We guess it's close to 80%, but we don't know. So see the tension now? We know this is 80%. We don't know what this is. We hope and think it's close to 80%, but we don't know. So there's just some number out there that is the percentage of people that would be helped by this drug, and we don't get to know what it is. See the tension? Now, that said, the point of this study was most likely inferential. Why? Well, because they're not trying to sell it to those 5,000 people. They want to sell the drug to everybody, right? So the company wants to sell the drug to all people with hypertension, right? So descriptive just is trying to describe what you see in the 5,000. Inferential is when you're trying to infer about the population to all people with hypertension. So they'd like to take their sample statistic of 80% and infer that it's like that for the whole population. Of course, I think they'd like it to be higher than 80%, but that's a whole other discussion. They'd like to infer about the whole population of all people. Not just the 5,000 in their sample. Now, that said, do descriptive statistics and inferential statistics go together? Oh, yes, right. We collect and analyze, right? So descriptive statistics is kind of on this side, right, when you're gathering and collecting and organizing that information. But often we use those descriptive statistics to make the inferences and draw the conclusions that we want. So it's not to say that you can't have descriptive statistics involved. You will. You kind of always do, to be honest with you. It's just we don't always make inferences. But the point for this company would be to make that inference and sell that drug to everybody. That's their goal. So that would be the inference they would want to make.